Alright, dear children, today we are continuing the chapter Work, Energy and Power, and we are going to discuss the Unit B of the chapter, different forms of energy. Alright, so here before we study different types of energy such as solar energy, heat energy, light energy, geothermal energy, nuclear energy, wind energy, tidal energy, etc. In physics we must first learn in detail about mechanical energy. So let's see, let us try to understand what is mechanical energy actually. Okay, so suppose you have a body and it possesses energy. All right, it possesses energy due to its state of rest or of its state of motion. Such energy possessed by a body is called mechanical energy. Now, mechanical energy are of two forms. All right, you can divide or categorize mechanical energy into two types. Okay, number one is potential energy. Okay, and number two, the second type of mechanical energy is kinetic energy. Now, potential energy can be further categorized into two groups. They are gravitational potential energy and elastic potential energy. Similarly, kinetic energy can be divided again into three types. Okay, they are translational kinetic energy, rotational kinetic energy, and vibrational kinetic energy. Okay, so now let me explain you. Okay, what is potential energy first. Now, potential energy is the energy possessed by a body due to its state, okay, of rest, due to its position, or there is a change in its shape or size, that is, there is a change in configuration. Such kind of energy possessed by a body is called potential energy. Alright, potential energy is denoted by the letter, capital letter U. Alright, now that is your potential energy. Now, potential energy, I said you, it can be of two types. One, okay, is gravitational potential energy, and the other one is elastic potential energy. Now, gravitational potential energy has something to do with height. All right, and elastic potential energy has something to do with the shape and size of the object. All right, now let me explain them one by one. Now, gravitational potential energy, as the word gravitational is there, now you know that whenever some object is lifted up, okay, in the upward direction from the earth's surface, what happens? The gravitational force tries to pull it down. Means as you are lifting an object up, what is happening? It is like you can say the energy is stored in it. All right, or you are spending some energy to lift that object, isn't it? Because you're applying some force against the gravity to lift it up. So you are doing some work on the body, and that work which you are doing on the body gets stored in the form of potential energy because you are lifting it to a certain height. So the height factor is actually helping the body to what? Gain the energy, and that kind of energy possessed by a body due to the height is called gravitational potential energy. All right, are you getting my point? You can take one example. For example, if you see you are like trying to break a stone, then you will be taking a hammer, isn't it? You will be lifting a hammer up against the gravity, and then when you leave that hammer, what will happen? It can strike on the stone and break the stone. Means you were storing some energy in the hammer. All right, and because of its height. So the energy is stored in a body due to the height, okay, or its position. That energy is called gravitational potential energy. Now, the second type of potential energy you can consider is elastic potential energy, and this is the energy possessed by the body due to the change in the shape or size of the object or the body. For example, if you take a spring, okay, if you compress the spring, what happens? Energy gets stored in it, and when you leave the spring, what will happen? it will again regain its shape, isn't it? Means it has some energy stored in it due to its change in shape. Are you getting my point? So here you see that the energy gets stored in the spring when you are compressing it, means you are changing its shape. Are you getting my point? So this energy stored, such kind of energy stored in a body due to the change in its shape is called elastic potential energy. All right. Now you can take another example, that is catapult, catis. Isn't it? There is a rubber band. When you pull the rubber band, means you are stretching the rubber band, means you are changing the shape of the rubber band. What happens? You are storing potential energy in it. How? By changing its shape. So when you leave, what happens? It can push the stone which is placed in the catapult in the forward direction. So such kind of energy is stored in an object due to the change in its shape or size, which we call together as configuration, is called elastic potential energy. All right. Now let's go to the next kind of mechanical energy, that is kinetic energy. Now as I said you, kinetic energy is denoted by capital letter K, and as I said you, it can be categorized in the three types. They are translational kinetic energy, rotational kinetic energy, and vibrational kinetic energy. And I guess by the word itself you can realize what kind of energy, okay, are they, or in what form they possess this kinetic energy. Number one is translational, means the body is getting translocated from one point to another. Understand? So it means that, see, okay, before I go to these types, let me first tell you what is kinetic energy. So kinetic energy is possessed by a body when the body is in motion. All right. Yes, here potential energy was the energy possessed by the body when the body was at rest. Are you getting my point? So here in kinetic energy, as I said you, the energy possessed by the body when the body is in motion, isn't it? Means body should be changing its place. Are you getting my point? And hence we have these three types of kinetic energy. They are translational kinetic energy, rotational kinetic energy, and vibrational kinetic energy. As the word says, translational, the body is getting translocated from one point to another. All right, means the body is in motion and the entire body is getting transferred from one point to another. So the kinetic energy possessed in it is called translational kinetic energy. For example, when you are in a car, okay, or a car which is moving in a straight line, or when you kick a football on a football field, what happens? When you kick the ball, what happens? The ball gets sets itself in motion and it gets translocated from one point to another point in a straight line. Such kind of energy possessed by a body is called translational kinetic energy. The other one is rotational, means it is rotating about a fixed point, okay, called an axis. So when a body rotates about an axis, the motion is called rotational motion, and hence the energy stored in it will be called as rotational kinetic energy. For example, you can see a fan, ceiling fan, isn't it? Yes, the blades in a mixer grinder, or you can see a washing machine. Inside the washing machine, what happens? The washing machine like spins about its own axis, right? So energy possessed in those bodies which are rotating about its own axis is called rotational kinetic energy. All right. Now the last and the third, okay, third and the last kinetic energy is your vibrational kinetic energy. So the word vibrational means the body is vibrating, body is moving to and fro. For example, if you take your scale or ruler, place the ruler on the edge of the table, okay, and fix this with your thumb and plug this end, the free end of the ruler. What happens? It starts to vibrate. It moves to and fro with a to and fro motion, isn't it? So such kind of energy possessed by your body is called vibrational kinetic energy. All right, you can see many examples like there's a strings of a guitar. All right, that is one example of vibrational motion. All right, similarly, molecules in an object, okay, are always in random motion. Yes, they are in actually I wanted to say about the molecular structure of solids. In solids, the molecules are tightly packed, so they can just move in their mean position, means they are having vibrational motion. Okay, and since they are in motion and they are vibrating, so the energy possessed by them is called vibrational kinetic energy. Is that okay? Are you getting my point? So let me recall again. Mechanical energy is the energy possessed by a body because of its rest or its motion. Okay, are you getting my point? Mechanical energy are of two types: potential energy and kinetic energy. Kinetic energy is denoted by the letter K, and it is the energy possessed by a body when the body is in motion. Potential energy is the energy possessed by a body when it is in rest. Alright, it is rest because of its height or because of the change in the shape or size. It is denoted by the capital letter U. Potential energy is again are of two types: gravitational potential energy and elastic potential energy. Similarly, kinetic energy can be broadly again classified into three categories. They are translational kinetic energy, rotational kinetic energy, okay, and vibrational kinetic energy. All right, I hope you understood here. Now let's go to the next topic, that is expression for potential energy. See, whenever we learn something in physics, you all know that we must be able to express in mathematical form. So now we are trying to see the mathematical form of potential energy. Now, as we have learned in the earlier unit, that energy and work, they are interrelated. You do work by spending energy. Okay, by spending energy you do work. So you can consider that energy spent is equal to work done. That is why the unit in which energy is expressed is joule, and the work is also expressed in a unit joule. So you can consider them as equal or same. All right, so here you know that the expression for W, that is work done, is given by F into S. We have done this in the earlier lessons, isn't it? So here, in place of work done, I can use it as potential energy equals to what is force. Force, okay, force is here, see, potential energy, the expression is given, okay, in the earlier heading also I have given you the expression, this expression here. You can see potential energy is mgh, kinetic energy here is half mv square. So now we are going to derive this. Okay, we are going to see how we got that potential energy is mgh and how your kinetic energy is half mv square. All right, so let's see here. So now, as you know, that work done is equal to the energy spent in doing it. All right, so we know that W is equals to F into S, and here work done is equivalent to the potential energy stored in it, and it can be given by the product of force into displacement. Now, since you see that he suppose say this is my ground, okay, and this is my body, I am lifting this body to a certain height, that is h. So I have to apply force on this. So force here is given by the product of the mass and acceleration due to gravity. All right, and the displacement here is h. So here I can replace this F with mg, okay, into the displacement here is the height, so mg h. So I get the relation for potential energy as U equals to mg h. Okay, now we are going to see the expression for kinetic energy. In the above slide, you saw that kinetic energy is given by the expression K is equals to half mv square. So now we are going to see this relation, how we can derive it. Now for this, you have to assume that there is a body, okay, of mass m moving with initial velocity, okay, v, initial velocity v, okay, and it is brought to rest. It is brought to rest by applying a force F. Okay, rest means 0. Its final velocity will be 0. Its initial velocity is v. All right. Yes. Now you see that the body was moving with initial velocity. Now you're applying a force to stop it, okay, means the body will have some retardation, isn't it? So let the retardation be A. So you get that F equals to ma from Newton's second law here. Are you getting my point? Now if you use the equation of motion, second equation of motion, you get that v square equals to u square plus 2as, isn't it? Or you know here that the final velocity is 0 and initial velocity was v, so v square plus 2as. Or from here you will see that minus 2as will give you v square, or s will be your v square by 2a. Okay, so here you will have minus. So here this minus sign is just to indicate that it is retardation. There is a negative acceleration. So now here we have the value for s. Now why we are finding the value of f and s? Because you know that work done is given by f into s, and now here the work done is what? That is kinetic energy. So kinetic energy is equals to force, here is ma into s is v square by 2a. So a and a gets cancelled here. So here I get mv square by 2, okay, which I can write as k equals to 1 by 2 into mv square. So I get the relation for kinetic energy, that is half mv square. All right. Okay, now let's move to the next topic, that is relation between kinetic energy and momentum. Now why we are trying to relate them here? See, you saw here that kinetic energy is equals to half mv square. See, you are using mass, you are using velocity here. Similarly, your momentum is given again by the product of mass and velocity. So here you see that in both the cases you are actually getting the product of mass and velocity. So how you can relate these two? That is our question. Alright, that is why we are trying to find, or creating a relation between kinetic energy and momentum. Alright, are you getting my point here? So from here what you can get is, you can get the value of v here. So now from this equation, if this equation is number 1 here and in number 2, from equation number 2, if I try to get the value of velocity, I'll get v is equals to momentum divided by mass, isn't it? Now if I replace this value of velocity in equation number 1, then I'll get k is equals to half m into, what is velocity here? Velocity is momentum by mass whole square. So I'm replacing this v with the value here, p by m. So now when I expand this, I'll get m into momentum square by mass square. So one mass and one mass gets here cancelled. So I'll have k equals to p square by 2m. Are you getting my point? Or when I make cross multiply, I will get, okay, 2 in twice of mass into kinetic energy. Or if I just leave my momentum on the left hand side, the square goes on the other side and forms square root. So I'll get twice of mass into kinetic energy under root. So this is the relationship between momentum and kinetic energy. So very important relation. Okay, so this is your first assignment today, to derive the relationship between kinetic energy and momentum. So the question number 1 for today's assignment is derive the relationship between kinetic energy and momentum. All right. Okay, so now let's move to our today's last topic, that is work energy theorem. Okay, work energy theorem. Now what does this say? See, as I said you in the earlier slide, that work and energy are interrelated. It says that according to this work energy theorem, the work done by a force on a moving body in the same direction is equal to the increase in its kinetic energy. So now what does this mean? I'll try to explain you here. Suppose you have a body, okay, and the body is moving in this direction with certain velocity. Okay, so now this body will have some mass. Let the mass be m. Are you getting my point? And it's moving with the velocity v. So since this body is in motion, all right, so it will have the kinetic energy, and that kinetic energy will be given by half mv square, isn't it? Now what this work energy theorem says, that the work done by the force, now you are applying the force on this body which is already in motion in the same direction, so this is the direction of the motion, and in the same direction you are applying the force F. So what will happen? Its velocity will increase or decrease? Its velocity will increase. So its velocity will increase. Suppose the velocity is v1, so its new velocity will be k1 equals to half m v1 square. Now if you compare this equation and this equation, here you see that velocity v1 is greater than the initial velocity v. All right, now because of this reason, you see that k1 kinetic energy becomes more. Okay, the new kinetic energy k1 becomes more or greater than the initial kinetic energy. So here it says that increase in its kinetic energy. So this is what we call work energy theorem. It says that the work done by the force on a moving body is the same direction is equal to the increase in kinetic energy. Okay, increase in kinetic energy. What is equal? Work done. So here you can write that work done equals to final kinetic energy minus initial kinetic energy. जति बढेको थियो नि त्यो kinetic energy, जति बढ्यो नि त्यो बढेको kinetic energy चाहिँ के हो? Equal हो कोसँग? Work done. कसले गरेको यो work done? By the force that you have applied. Are you getting my point? So let's read the work energy theorem again. According to this work energy theorem, the work done by the force on a moving body in the same direction is equal to the increase in its kinetic energy. All right, so I hope you understood. Now we have a little more to do in this chapter, okay, particularly in this unit, which we'll do in the new class, or in the next class, in the new video. All right, okay, so before I conclude today's session, okay, let me give you, okay, so we have, okay, wait, we have one more topic to be discussed here, that is conversion of potential energy into kinetic energy. So here I have said here that potential energy changes to kinetic energy whenever it is put into use. So whenever you are using potential energy, that is you, okay, you cannot use potential energy directly. It has to be first converted to kinetic energy to make use of it. For example, height. Suppose this is the ground, this is an object, okay, or this is a stone which I want to break. So I have to take a load, okay, up to a height. Suppose say I am taking a hammer, okay, I am taking a hammer. I have to raise the hammer to a certain height. So at this height, it has potential energy, that is mgh. Now this potential energy cannot do any work until and unless I leave this hammer or I hit with this hammer, isn't it? So when I leave the hammer falls down here. So when the hammer is falling down, what happens? Hammer now sets into motion. Now whenever something is in motion, it has kinetic energy. So this potential energy is now converting into kinetic energy to do the work. So what I am trying to say here is that potential energy always gets converted into kinetic energy before it does some work. Okay, that was the explanation with height. Now the other one is with spring. All right, so I have a spring here and I have a ping pong ball, or you can use a TT ball, okay, table tennis ball. I compress this spring now. So when I compress the spring, the size of the spring gets reduced, isn't it? Now what happens? Due to the change in its size, or you can say shape, it has potential energy in it. Now until and unless I leave it, it will not do any work. But as soon as I leave it, what will happen? It will again come back to its original shape or regain its shape, and it will what? Expand, isn't it? So when it is expanding, it will set itself in motion. Now whenever you have a body which is in motion, it has kinetic energy. So here the spring is doing the work. How? By converting the potential energy stored in it during its compressed stage into kinetic energy when it is released. All right, clear? Similarly, your string also. Okay, string, suppose for a string, when you come across this word string, okay, let me take one example of bow. Let me take the example of bow. So here what do I have? I have a bow. Okay, this is the string of the bow, dhanu. Okay, so when I pull this string, what happens? I'm changing its shape, isn't it? Now it has stretched. Now when this body is stretched, it's changing the shape, so the energy stored in it is potential energy, that is U, isn't it? U is the letter that we denote potential energy. So as I leave this, what will happen? It will again regain its original shape. So when it regains its original shape, it sets itself into motion, and again you see that here the body is in motion, so it will possess kinetic energy. So here the potential energy stored in this string of the bow gets converted into kinetic energy before it does the work, that is before it pushes the arrow in the forward direction. So here you see that potential energy, whenever you are trying to make use of that potential energy, it always changes into kinetic energy. All right, so you cannot use potential energy directly. You always have to convert potential energy into kinetic energy to make use of it. So what I'm basically trying to say is that potential energy can be used only after it has converted into kinetic energy. All right, so that's all for today. So before I wind up, I'll give you some assignment. The first assignment that I gave you was to derive the relationship between kinetic energy and momentum, isn't it? Yes. Now the other assignment for today is to classify mechanical energy. You know mechanical energy are of two types. Okay, then define number one is potential energy and number two is kinetic energy, and also write their expression, that is mgh for potential energy and half mv square for kinetic energy. So these three are your assignment for the today. All right, so that's all. Thank you.